Welcome to our group theory lecture. Today, we are going to explore one of the most fascinating and powerful ideas in mathematics, known as Fermat's little theorem. Imagine a magical combination lock where spinning the dial a specific number of times always brings you perfectly back to the start. This theorem is exactly that, but for numbers. It might sound like a neat party trick, but it is actually a profound rule about how numbers wrap around themselves when we divide by prime numbers. Let us dive in and see how it works. To understand Fermat's little theorem, we first need to think about modular arithmetic, which is essentially the math of remainders. Imagine a clock face, but instead of 12 hours, it has a prime number of hours, which we will call p. When we count past p, we simply wrap around back to the beginning, just like a clock resets after 12. In this system, when we take a number and repeatedly multiply it by itself, raising it to higher and higher powers, the remainders do not just bounce around randomly. They actually create beautiful, predictable cycles. Understanding these cycles is the key to unlocking shortcuts for massive calculations. Now that we understand the idea of clock math, let us look at the formal mathematical statement of Fermat's little theorem. The theorem states that if you take any integer a and raise it to the power of p minus 1, the result will always leave a remainder of exactly 1 when divided by the prime number p. Here, a is our base integer, and it must not be a multiple of p. The symbol with 3 horizontal lines means is congruent to, which is just a formal way of saying leaves the same remainder as. So if you increase the prime number p, the exponent grows, but the final remainder after division is always magically stripped down to 1. Before we move on, let us see this with a concrete visual example. Here we have a modulo 7 clock, meaning our prime number p is 7. We are looking at what happens when we repeatedly multiply by our base number, 3. Starting at 1, multiplying by 3 takes us to 3. Multiplying by 3 again gives 9, which wraps around our 7-hour clock to land on 2. If we follow the black arrows, we visit 6, then 4, then 5. Finally, the red arrow shows our 6th step. Multiplying 5 by 3 gives 15, which wraps around to exactly 1. Just as the theorem promised, taking 3 to the power of 6 brings us perfectly back to a remainder of 1. Now that we have seen the visual cycle, let us use the formula to solve a real problem. Suppose we need to find the remainder when 3 to the power of 31 is divided by 7. Calculating 3 to the power of 31 directly is a nightmare. It would overload a standard calculator. Instead, we identify our prime p as 7 and our base a as 3. Since 3 is not a multiple of 7, the theorem applies perfectly. The theorem tells us that 3 to the power of 6 is congruent to 1 modulo 7. We can use this as a shortcut. We divide our massive exponent, 31, by our shortcut exponent, 6. This tells us that 6 goes into 31 exactly 5 times, with a remainder of 1. Continuing from our division, we can now break this terrifying problem into much smaller, manageable chunks. We rewrite 3 to the power of 31 using the pieces we just found. It becomes 3 to the power of 6 raised to the 5th power multiplied by 3 to the 1st power. Because we know from Fermat's little theorem that 3 to the power of 6 is just 1 in our clock math, we substitute 1 into the equation. The number 1 raised to the power of 5 is simply 1. Multiplying that by 3 gives us our final answer of 3. So without ever calculating the gigantic number, we know with absolute certainty that the remainder is exactly 3. Let us solidify this with another example, reducing an even more massive exponent. We want to calculate the remainder of 2 to the power of 50 when divided by 13. Again, we identify our prime p as 13 and our base e as 2. Since 13 does not divide 2, we are perfectly safe to use Fermat's little theorem. The theorem states that 2 to the power of 12 will be congruent to 1 modulo 13. We will use this fact as a mathematical scalpel to cut down the massive exponent 50. We divide 50 by our shortcut exponent 12. Doing this division, we find that 12 goes into 50 exactly 4 times, leaving a remainder of 2. Picking up from our division, we split the exponent 50 into 4 blocks of 12, plus 2 leftover powers. Using standard algebraic rules, we rewrite 2 to the power 50 as 2 to the power 12, all raised to the 4th power, multiplied by 2 squared. We then replace the 2 to the power 12 portion with 1 because of our theorem. This immediately collapses the giant number into something you can calculate in your head. The 1 to the power 4 disappears, leaving only 2 squared, which is 4. Therefore, the remainder when 2 to the power 50 is divided by 13 is exactly 4. This technique turns an impossible calculation into basic arithmetic. Now that we have used this formula to solve problems, let us understand where it actually comes from. Since we are studying group theory, we must look at this through the lens of mathematical groups. If we take the set of numbers from 1 up to p minus 1 under the operation of multiplication modulo p, they form a valid mathematical group. Because p is prime, every number in this set has a multiplicative inverse, meaning you can always multiply it by something to get back to 1. We call this the group of units modulo p. The total number of elements inside this group, which we call its order, is exactly p minus 1. Let us begin the formal proof of Fermat's little theorem. We start by picking any element A from our group of units. In group theory, the order of an element is defined as the smallest power you must raise it to in order to get the identity element, which is 1 in this case. Let us call the order of our element A by the letter k. This means A to the power of k is congruent to 1. Now we bring in a heavy hitter, Lagrange's theorem. This theorem states that the order of any single element must perfectly divide the total order of the entire group. Since our group's order is p minus 1, k must divide p minus 1. Continuing our derivation, since we established that k perfectly divides p minus 1, we can express p minus 1 as some integer multiple of k. Let us call that integer m. So p minus 1 equals m times k. Now let us look at the expression we are trying to evaluate, a raised to the power of p minus 1. We can substitute our new expression for the exponent, rewriting it as a raised to the power of m times k. Using basic rules of exponents, we can pull the m outside the parentheses, giving us a to the power of k, all raised to the power of m. This sets us up perfectly for our final substitution. We are now ready for the final result. Recall that we defined k as the order of element a, which means a to the power of k is congruent to 1 modulo p. We can take that 1 and substitute it directly inside the parentheses of our expression. This leaves us with 1 raised to the power of m. Since the number 1 raised to any power is still just 1, the entire expression simplifies perfectly. We have successfully shown that a raised to the power of p minus 1 leaves a remainder of 1. This shows the incredible power of group theory. A profound result about prime numbers falls out naturally just by looking at the sizes of groups. So, we have proven that this theorem holds. This brings us to an important question. Why does anyone care about remainders of massive numbers in the real world? It turns out Fermat's little theorem is actually the invisible shield protecting your digital life. It forms the mathematical foundation of the RSA encryption algorithm, which secures credit card transactions, emails, and secure websites. When your computer talks to a bank, it uses massive prime numbers and exponents to scramble your data. Without the shortcuts provided by Fermat's little theorem, computers would not have a fast, reliable way to encrypt and decrypt these messages, making modern internet security completely impossible. Let us summarize the key takeaways from today's lecture. We learned that Fermat's little theorem is a powerful tool that simplifies massive exponents in modular arithmetic. By using the formula a to the power of p minus 1 is congruent to 1 modulo p, we can break impossibly large calculations into manageable cycles. We also saw how this beautiful bridge between prime numbers and group theory is proven using Lagrange's theorem, showing that it is a fundamental property of mathematical groups. Finally, we discovered that this simple rule is what makes modern cryptography and secure internet communication possible. You have now mastered a truly foundational concept in mathematics.